All right, so with this background, let's understand a little more about this process of phase separation. Okay, and in order to understand it, let us look at that curve again. Okay, let us get back to this free energy curve. Okay, we have this non-convex shape. Okay, and let's now look at the region over which we have over which the free energy actually is non-convex, right? So it is in this region that we are seeing, that chi double prime is less than 0. Okay, and what that means is that simply the second derivative of the curve is negative there, right? The curvature is negative. Okay, all right, we know that. So let's see what's going on there. First of all, let me state that the region of the curve where the second derivative is negative is sometimes called the chemical spinodal. The region of the curve where okay, that's called the chemical spinodal. This region is called the chemical spinodal. Now, what happens here is the following. So over this chemical spinodal, consider our formula for the flux. Okay, and this is something we wrote out last time by going to non-equilibrium thermodynamics. Okay, so consider the flux. Okay, and what we wrote then was that the mass flux is equal to minus a positive semi-definite mobility tensor grad mu, where mu is the chemical potential, okay, and is equal to that derivative. Okay? All right, we have that. Let us now go ahead and see what happens because of this chemical spinodal. Okay? What one can see is that it's actually fairly straightforward to write out this formula in the following form. It is gradient of mu, which we already know to be chi prime, right? This chi is a function of c alone, so derivative of chi with respect to c is chi prime. Okay, but then if we want to compute that gradient, we see that it is now minus m. Gradient of chi prime is chi double prime gradient of c from the chain rule, right? Okay, but now what happens in the chemical spinodal? Chi prime is less than 0 in the chemical spinodal. All right. As a result, if m is positive if m is positive semi-definite, right? Chi prime is less than 0 in the chemical spinodal, and we know that m is positive semi-definite. Okay? All right. What this means is that the fact that chi prime is less than 0 essentially negates this other negative sign. Okay? And as a result, what we are seeing is that J is, J becomes sort of proportional to gradient of C. Okay? Something like this happens. This last result that I've written becomes clearer. Okay? It becomes clearer to see if you consider the mobility tensor M to be just some scalar value M times the isotropic tensor. Okay, this is a special case of mobility. This is the case where the material has equal mobility in all directions, where it is isotropic. Okay, so this is isotropic mobility. Okay, in this case, what happens is that J is equal to minus M isotropic tensor chi double prime gradient C, all right, which is basically minus M, which is a scalar now, chi double prime gradient C. But now this quantity is greater than 0, greater than or equal to 0. Okay, so we see that the flux is essentially proportional to gradient of C. Okay, what does this mean? What this means is the following. Okay, in order to understand what this means, let us briefly consider classical mass transport in 1D. Okay, 1D just to be able to fix ideas. Let us suppose that we have a concentration distribution C, which is uniform everywhere except maybe for a little bump somewhere. Okay? Now this is the sort of situation that happens where if you take a beaker of fluid and introduce a drop of ink in it, what you've done is that over the region of that drop, you've increased the concentration, right? You've increased the concentration of the ink. The ink has 0 concentration everywhere else except at this point where I put a drop of ink, right? So there's a little bump in concentration. What happens? We know that as time progresses, right, that concentration tends to smoothen out, right? So we get something like this. We get a much more gentle bump, right? Okay, and this has to do with the fact that for conventional diffusion, what we have is that the flux is equal to minus M gradient mu. Okay, this thing essentially leads to a formula where J equals, if in the case that we had before, what we're seeing is that this is equal to M chi double prime gradient C. If chi double prime were greater than 0, which would happen if our free energy were convex everywhere, okay? If the free energy were convex everywhere, chi double prime would be greater than 0, and therefore what we would have is that at any place where we increase the concentration, there would be a tendency for the flux to drive the concentration downwards, right? There would be a tendency for material to move from high concentration to low concentration, okay? And that is because if M were positive, if M were greater than or equal to 0, chi double prime were greater than 0, what we see is that J is proportional to minus gradient of C. Okay? And as we discussed in a previous segment, this is what tends to cause material to move from high concentration down into lower concentrations, regions of lower concentration. And so this would happen, right? The region of high concentration would sort of dissipate away, would diffuse away, because material would move to lower concentration regions, right? And then later in time too, what you would see is that things would finally maybe have a slightly higher overall concentration, right? But it would be smooth, okay? If chi double prime were greater than 0 everywhere. Now we have a different situation, okay? But now we have chi double prime is less than 0 in the region of the chemical spinodal. So it means that if concentration lies in this chemical spinodal, here's what happens. You start out with concentration with a slight bump. Okay, like there. What will tend to happen is that instead of material moving from high concentration to lower concentration regions, the opposite happens. Okay? All right? So if this little bump of concentration were to take the C, right, the concentration in this at this point into the chemical spinodal, right, what would happen is that material would not move from high concentration to low concentration, but would go the opposite way. Okay? So as time progressed, you would see this happening. That bump would grow. I made that bump a little too broad. That sort of thing would happen. Okay? So you would effectively have material moving uphill. Okay, you would have uphill transport. In 1D, okay? But it happens in higher dimensions as well. This is just the way we describe it in 1D. Well, what happens then is that suppose that regions really sort of phase separate, right? Because the rest of the material will develop a lower concentration. There will be some small region with a higher concentration. Okay? And what this leads to is phase separation. Okay? Let me draw for you a picture to show you what happens if you were to look at this thing in multiple dimensions. Okay? So if you were to look at this phenomenon in 2D, right? I won't try to represent 3D here. So supposing we had our continuum body, omega, okay? And what I'm going to say is that suppose the concentration everywhere was uniform, except in some small region around it. So let's suppose that concentration everywhere were uniform, except that you would introduce some small little perturbations, right, in some places, right? And I'm drawing these little green islands to suggest that there are little perturbations in concentration. Okay, and I'm going to say that okay, these little green islands. Okay, And now let's suppose that we had, and suppose those little perturbations in concentration were such that they took us into this regime of the chemical spinodal. Perturbations from uniform concentration in the chemical spinodal regime. Okay? What happens then? Over time progresses, right? And let me see if I can draw the body again looking roughly the same. Well, not quite, but okay. Nothing has really changed as far as the body is concerned. It's still omega. The shape hasn't really changed here. Let me try to draw that better actually. Okay, a little better. What will happen is that these regions with perturbed concentration will grow. Okay, just as we showed in the 1D case. So those little regions will grow. Okay, and as they grow, the concentration around them will decrease, just as we showed in the 1D case. Okay, these regions will grow, whereas the concentration around them will decrease, and the material will phase separate. Okay, so we have phase, and just to demonstrate that we really have phase separation, I'm going to use both colors here. Okay, we have phase separation. Okay, this is how phase separation happens. All right, we're going to stop here for this segment, and when we come back, we will understand more about the mathematical treatment.